Log on, tune in, find out. Another good idea from Cambridge.
Here today about, so I took your email serious when you said that you want an informal talk, so this is very informal, so especially for the people watching on TV, don't do this at home. But this is joint work with a student in Sydney, David Lewis. He's an undergraduate student. We've been doing this in the past year, I suppose. We are concerned with a general question that we have. Let's imagine we have a huge dimensional system, and that involves some scale separation, time scale separation, so we have slow variables and fast variables, and they're coupled in any particular way, and the system can actually be deterministic and or can be stochastic. Our specific aim would be that's our long-term goal, to consider deterministic systems of this kind, and then we're interested in distilling the dynamics of the slow variables only. So we want a consistent reduced equation for just the slow variables. And then just to sort of go in line with Mike's talk yesterday, then of course we have to make sure just that we know that we've derived equations that are close in some asymptotic sense. Doesn't mean that the solutions actually have anything to do with each other. But the methods I'm going to present, there's this theory, there's some rigorous theory that exists there, it's out there. And then the question is, let's assume that, so we can split our state space, and we have the slow variables and the fast variables, and let's say that the fast variables are chaotic. So the question is, can we model, can we then have a reduced equation that is stochastic? So can we model the fast chaotic processes by some noisy process? So this is a general framework. We're not going to arrive there, but I'd like to present somewhere that we went. And so some of you will recognize this little toy model. That's one of my favorite toy models that was introduced by Marcel Oliver. So Q, think of Q as a position. Then this is an equation of motion for a particle with a small mass epsilon. And then you can think of the JQ dot term as a magnetic term. So let's say you have a charged particle in a magnetic field. So this would give you some gyrations. And then we have an ambient potential V. Or since we're doing climate here, let's put this into more of a fluid context. You can think of this equation as a caricature for shallow water in the semi-geostrophic limit. So just a quick motivation here. So the two equations up here are the shallow water equations, where I've written it with this material derivative ddt. If we do some scaling, similar to what Mike was talking about yesterday, and introduce a Rossby number epsilon, and we introduce a Borges number b, then we end up with this type of equation. If we now say, you can almost see this equation. I should actually write it down here. That so you can recognize this equation here. That's the Coriolis force here. That's the J term. And if we now say, which is of course unphysical, but if we say, well, okay, we prescribe the layer depth, so we ignore that the layer depth is actually coupled and evolving, but we prescribe the layer depths, then this one here is a caricature of the semi-geostrophic limit. We had the Borges numbers also of order epsilon here. Okay, so let's see what this model is. More, we can rewrite this model in a Hamiltonian form, but we have so this is not a canonical coordinates. So this is a non-trivial Poisson structure. I mean, you can make it. You can transform it into canonical form, but then P equal to Q dot is not Q dot is not your momentum variable anymore then. And this system has scale separation. So let's look at the scale separation. On a fast time scale, the two terms that will balance, we get a 1 over epsilon squared from here, and we get a 1 over epsilon from this time derivative. So those are the two dominant terms on this 1 over epsilon order. And these are the fast, in the magnetic constants, the fast durations. Okay? So these are fast rotations, fast oscillations. However, on a small, on the order 1 time scale, on our t time scale, we may just ignore this inertia term here and have a balance between those two. Okay. And this is this our slow dynamics. T dot is minus j grad v. That model is good. Well, that is a good model provided that v doesn't, that the initial condition and the initial amount of kinetic energy you put into the system and your v are such that you don't have too much chaotic motion. So let me show you some numerical results here. So this is a contour plot in Q1, Q2 space. This is the potential. These are contour lines of the potential. So we have a convex potential. And we have in red the full dynamics, the full 4D dynamics. And in green, you can hardly see it. It's our reduced system, Q dot. So let's put epsilons here for the full system. And this is minus J grad V. So this is a reduced system. So think of V as a Hamiltonian. So Q just goes along equipotential lines here. So that's what you see, what's happening in here. And this assumes that I put my initial data of the full system such that this relationship is satisfied. So these are balanced initial data. If I don't do that, I generate these fast gyrations, fast oscillations around this slow manifold here. Okay. So that part is very well understood. Sebastian actually did some work with Colin Cotter on it in a Hamiltonian framework, showing convergence of solutions of this system and actually higher order balance models. I'm not going to talk about that now, just mention it now. And the full system, and Marcel Oliver and myself have done this in the Lagrangian framework. So that is well understood. However, if we now look for non-convex potential, and we look at a long trajectory here. So in green, again, you see the slow dynamics given by that equation here that just follows equipotential lines. But red is a projection of your full 4D system, and it fills this one up uniformly. So these are all the accessible states, and that they're all filled. So if we look at just the times here, so let's just take Q2, for example. Actually Q2. So in the regular case, you have these slow oscillations, and then you got your fast oscillations sort of around that. So these are the oscillations on the fast around the slow manifold. However, in the chaotic one, you get something that looks like this, right? I mean, it goes from one side of the world to the other one. So it looks stochastic. So I said at the beginning, what I really would like, and I also said that I haven't arrived there yet, is to have a deterministic system like this one, where we know there's some timescale separation. We discussed this, and we know there's some chaotic motion in there. There's some chaoticity there. Can we reduce this one into some stochastic reduced equation for just slow one? So replace this one here by an SDE. That's what I would like to do. And the way I would like to do that, and this idea goes back to Friedley and Wenzel, is you add some noise here. And this noise regularizes it, makes things that you have, an invariant measure, the unique invariant measure there, and you can do. So you introduce this regularizing noise, and then the hope is that if you take first the limit, epsilon going to 0, so that means you do some asymptotics to go to your reduced equations, then that will depend on your kappa. This equation here, this reduced equation, would depend on your kappa. And then if you then turn off the kappa, let kappa go to 0, that you still end up with an SDE. That would be the hope. And that's what we haven't, sadly, we haven't actually managed that. But we discovered something else that may be of interest, and that's where I would like some input today from the climate solutions.
Some damping, right? I mean, otherwise,
yeah,
energy will grow unboundedly in the system.
That's right. That's right. So let's exactly. So let's put some. So now we try this and we tried in one direction. That didn't work, but I still want to show you that direction. So this is now our system in rescaled in a rescaled form. So Q is in R2, and P is in R2. So this is our original system, and now we put some fast noise on it. So the noise on the same scale as the fast durations. Okay. So noise is fast, oscillations are fast, and then here we have our slow bits of the vector field of the dynamics. And what we would like to do here is, so if we want to do this spiel, this spiel of adding regularizing noise here and deriving some reduced SDE, then we thought, we better actually make sure that this noise doesn't destroy our energy conservation, because we've already seen that this one here, this is a Lebesgue measure. So you project everything down and you get the Lebesgue measure in the Q plane. So we want the energy to conserve so that at least this one will be reproduced by our reduced slow dynamics. So what we're going to do now is we're going to introduce some noise that will nevertheless assure that the Hamiltonian of the deterministic part is still conserved. And then we're going to do the reduction, and we're using stochastic singular perturbation theory to achieve this. Okay. So here you introduce some damping here, you introduce an Ornstein-Uhlenbeck process. So this is our system, but now we introduce this gamma here and the sigma. If we do that, then this will give you a Gibbs distribution, right? I mean, you will have, if you simulate this one, you will have something where the empirical density will be concentrated around the minima of your wealth. So that's not what we want. So we have to do something about this noise. And what we do is we add an auxiliary process, an auxiliary noise, Y, onto this one, or By. And now we want to choose S and B. So these are three parameters of our auxiliary noise. We want to choose them such that energy will stay conserved. So the first time I heard about how to do this was actually a talk by Zdzisław Brezhniak and also then by Ben Goldis. They work in a framework of Stratonovich dynamics. They just say, they just introduce some projector. I will talk to you about the projector in a minute. And then stay in the Stratonovich formulation. I'm here on ITO, and Erik van den Eyden has done something on that as well, how to constrain noise to some manifold. So aim is choose S and B such that the Hamiltonian will be conserved. Okay. So first thing we need is a projector. We need to project our noise. We'll have components. So that's our energy, our level set. Then the noise will have components that are orthogonal, that leave the energy surface, and it has some that go in here. This is our noise here, the noise that we introduced here is the Ornstein-Uhlenbeck process, right? Because there's no restriction on this Ornstein-Uhlenbeck process. So we want to choose now S and B to eliminate the components of the noise orthogonal to the manifold. Okay. So we introduce here a projector that projects actually just out of the onto the tangent plane of the kinetic energy. So on P transpose, on this one. And what we require is that this projector applied onto our auxiliary process gives us a 0. Because that one has only, our auxiliary process should only have components that leave the energy, make the dynamics leave the energy cell. So this is our requirement, right? We do not want to have any components of this actually that are parallel to the tangential bit. We use S and B, or this auxiliary process, only to kill off the orthogonal components. Okay. And we want energy conservation. So we require that dH is 0. How do we calculate dH? We use E to lemma. So if we apply E to lemma, then we get up some horrible expressions. And now we would like that sigma is 0 and mu is 0, and so dH is 0. So mu is a drift here, and sigma is some diffusion. Okay. So we can do this. Here, for example, you see already, you want this to be 0. So you want this one is orthogonal to the direction that's normal to your kinetic energy surface. Okay. So that's where the projector comes in. And so we get here expressions for ST and BT that now assure that the noise process we've added is now energy conserving. And if we now introduce the values for S and B into our system, we end up with this equation here. So we have here, you see, this is the core, our deterministic core here. But then we modify the Ornstein-Uhlenbeck process, so we project it, and we project our noise, and then we get an additional drift term. Okay. So that's also just so as a side remark, when you do Stratonovich, you will not see this drift term anymore. So this is its 1/2 here, right? The Stratonovich 1/2. So now what we would like to do, but actually before I should maybe show you, I think this is the next slide, yeah, that what we're doing really does, so this is some numerical simulations of this system that I've just shown you, this system that's augmented with this auxiliary process, and this is the energy, or the energy loss actually, as a function of time, very long times, and this is 10 to the minus 5. So we have gradual systematic loss of energy, however, very, very small. And the loss is, this is finite, this is finite size, finite discretization effect. Because if I use this was done with an Euler-Maruyama scheme, you always have a little component that leaves the exotangential plane. Okay, so that's expected, but it's very small. Okay, so we achieved the first step. We've achieved to introduce our parametrization of our noise that conserves the Hamiltonian. What we'd like to do now is from this system, so this is our system from which we start, to derive from this system a reduced equation. And in order to do that, we don't want to work with this SDE here that's nonlinear. We want to work with a linear PDE with the backward Kolmogorov equation. So we have to introduce the generators associated with this SDE. So I've written them down here. And then you crank back.
This is Ito or Stratonovich?
Ito. I'm Ito.
You're Ito.
Yeah.
And you said the half this nasty bit would go if you go to Stratonovich, is that?
Yeah, there's always this 1/2. This
because
prime.
Stratonovich would, in this case, would be the more natural thing, right? Because you just project everything.
That's right.
Right.
You can do it either way. You can, Ben Goldis and Brezhnev, they always work in the Stratonovich thing when they project.
What you naively would do, just project, right?
Yeah, this is what I do. I just project.
Well, just apply this projector to all the terms you had before.
And then interpret this as Stratonovich.
Yeah, so if you take your original equation and just apply your P, your projector.
Onto the equation and interpret this as, yes.
Then it's...
That's right. You have to be a bit, this is a bit fiddly. There's another P coming in there, I think, if I remember correctly. Where you put the dot is another little circle. But yeah, you're right. This is just projection. Okay. So now we calculate the generators, and we crank the handle. So this is our backward Kolmogorov equation. The strategy is now, for V, we make an asymptotic expansion. Then we insert this into here and collect powers of epsilon and solve for successive orders. What we need to do here is we need to assume for the lowest, for the fast, noisy process that we added, we need to assume some ergodicity. For this stochastic process that we added here, this is the case, and you can prove that. So we assume that always has to be assumed, right? I mean, for this method to work. And then so we crank the handle, and then what we're after is an evolution equation here for the lowest order. And then we go back from this reduced backward Kolmogorov equation to an equivalent large line equation, STE. And there's some theory by Kurtz from the 70s that shows that actually then the solutions are also close. Yeah. Okay. So the lowest order problem, so the fast one, is just that L naught, V naught is equal to 0. We said that, or that we need that the fast dynamics is ergodic. So this L naught here only depends on the fast variables, on the P's. Okay, so there are all these dP's in here acting on V naught of Q PT. So an obvious solution is that V naught only depends on Q. And because it is ergodic, this is the only solution. There is no other solution that could depend on Y. Think of this V naught at expectation values. So if it would depend on Y, the system would not be ergodic, but we assume that, or we actually prove that it's ergodic. So this solution here that only depends on Q is the only solution possible. Okay? And that's then what we're after. This is already a reduction. Our lowest order now only depends on the Q variables. Okay? So if we get an evolution equation for V naught, we can then derive a reduced STE. So that's our gain now, our goal. At the next order, you get this problem here. So now at every order, you have this linear eigenvalue problem here. So we have a solvability condition. We have to require that the right-hand side here is orthogonal to kernel functions of the adjoint of L naught. So the adjoint of L naught is the function that's associated with the densities, how you propagate densities. So L naught star, I should write star. So we have the formal L naught star operator, rho equal to naught. So this is then rho is a kernel function. But again, because of so Fokker-Planck equation would be this. So again because of ergodicity, there's only one. There's a unique solution, unique invariant dt rho solution of this equation. So there's a unique kernel function, which we denote with rho infinity, which is the solution of, it's empirical, it's a density, it's a measure induced by the fast process, by our lowest order process. Okay? So we just average this right-hand side over this invariant density here, rho infinity, and because it's an Ornstein-Uhlenbeck process, what we put in, this is 0, or roughly an Ornstein-Uhlenbeck process, this is 0. Yeah? So V1, there always exist solutions V1, which is good. And we can we can solve this equation, and that's what you get here, where RQ, we can always add a function RQ here that lies in the kernel of L naught. And we can choose this one then such that the expectation value of V is just V naught up to our asymptotic order. So we can play with, here we have some freedom to make sure that we explain most of the expectation value with our V naught.
So why there?
Oh, why is this? I don't want to write this now. So that's just why is this a terrible expression here? This is a p squared here. So you can express p squared as a function of q using your Hamiltonian, right? So whenever you see p squared, it doesn't mean it's a function of p, it's actually a function of q then. So, the next, the order 1 problem, this is what we're after, the dTV naught. So our solvability condition now is again right-hand side orthogonal to the kernel function, which is our invariant density induced by our fast motion. And this is our reduced backward Kolmogorov equation. So if we just sub this in, we end up with this equation here. And k is, I introduced this k here, which is p squared, which is now the function of q. And y is only then a function, y is capital Y, ignore what it really is, but it's a function of q, it's not important. So this is, this is our reduced slow dynamics. So the bad thing is, if you let sigma go to 0 here, so sigma was our initial, was like the strength of our stochastic process, so to speak, we do not get any non-trivial stochastic dynamics. So this was not good enough, what we've done, to actually get a non-trivial SDE as a reduced model. Okay. So what I really wanted to do, I didn't make. Okay. But I wanted to, oh, that's not visible. So what you should see here is the empirical density of the full system and the reduced system. So they look the same, which just means that the method works. But let's be a bit more specific here and measure the sojourn times. So how long, and measure the mean of them. So on average, how long do I stay on one side before I hop to the next side of the potential world? And in green here, this is epsilon as a function of epsilon. In green, this is the sojourn time of the full system, this one here, and this one, sorry, of the reduced system. The reduced system doesn't have an epsilon in it, so this is of the reduced system that's constant for all epsilons. And this is the sojourn time, the mean sojourn time as a function of epsilon for the full system here. Okay? And you see convergence, and the convergence is roughly with 2, consistent with the asymptotic order. So it works nicely. Now, what have we done? So we constructed a stochastic derivation which respects energy conservation of the full deterministic system. And this is where I would like the input. There may be some more useful system than this toy system, where this could actually be in the meteorological context or climate context, where this could be of use. So I'd like some input there on that. And then, because we know how to do that, then we can do what we've done, which is this singular perturbation theory, to derive the effective long-time dynamics, the slow variables. So this is where I would like some input here from you, and this one is, well, if you have an idea how to do that, but that's what I would like to do as well. Can we find a different projection, or can we construct a different regularizing noise so that we end up with a non-trivial SDE if we let this auxiliary noise that we just add for regularization purposes go to 0. So that I would really like to do. That would be lovely. Oh, well, yeah, and once we've done this, use all this machinery to attack some more useful problems than just this toy model. That's it. Thank you very much. Questions?
Well, it's, I think because you just have the fast motion is just a harmonic oscillation, right? So I think that's probably one of the reasons why you don't get any non-trivial reduced limit, right? Because
yeah, but that one is still, I mean, the chaoticity is not, it's spread over fast and slow variables, right? It's not just oscillations. I mean, there's some chaoticity in there as well, no? I mean, they're driven then by the slow.
It's just my experience with homogenization of fast and slow systems. If the fast motion is purely harmonic and the frequency doesn't depend on the slow variables, you don't get any interesting coupling. It completely decouples. But if you have fast motion or oscillatory motion and the frequency of that fast motion depends on the slow degrees of freedom, then you can get non-trivial coupling, actually highly non-trivial coupling.
I mean, the frequencies, I mean, you would expect that the frequency is just 1 over epsilon, right?
Right. Yeah,
but it's not. There is a back coupling to it. Like if epsilon is not very, very small,
but
the actual frequency is
yes,
but then it's constant. That's what you're saying. For fixed epsilon, I have it constant. Yeah. So you think there's not enough back coupling from the slow dynamics onto the fast? Yeah.
Actually, we can maybe talk afterwards. I mean, I've done some work on. You have stiff springs representing like.
Well,
and then you add noise to this. I mean, I didn't do it on the constant energy surfaces. I just did it in the canonical constant temperature setting, and then you get you can get quite.
But what I've done, I mean, a while ago actually, is I've taken the projection in the Q plane and I coarse grained the space, and I assumed that my reduced equation is some SD of this form, and then I have my trajectory in cross because it's just a projection, right? And then reduced means I have to coarse grain, and then I sample my trajectory, and then I look, I mean here, how do you get the dq? It's just, the q, like you need an average of the time derivative of q and at my box. So I do an average over all the changes here, and then I get an estimate here, and I mean, if you look at the quadratic thing, you can get one here if you're clever about how to choose your sampling time. And look, you get something out there. I mean, it's not. There are.
You did this for this model system.
Yeah. So that's how I started actually. To see whether there is actually, whether there's any hope of getting a stochastic reduction. But it is quite fickle to get non-trivial values here. It is very dependent on a right choice of your sampling time. There's a very narrow range of sampling times when you get this. If you choose this too large, I can't remember, I can show it to you. If you choose this too large, I think you always get a linear term here because it's basically just Markov, right? You just hop. Actually, I think, this is sort of standard procedure what people do, and quite often you see people saying, oh, well, this is just, they want an Einstein-Uhlenbeck process, or this is just negative. And I suspect that quite often they just chosen a too long sampling time.
You don't, it's not that you get this stochastic term just from the fast oscillations by...
No, it's far, the sampling time definitely has to be larger than the fast oscillations. So around 4 fast oscillations.
It shouldn't be too short, but it shouldn't be too long either.
That's right.
okay.
That's right. Exactly. Yeah. But yeah, maybe, because you need somehow that information sifts through, right, to the, and if the fast variable only does another. But this is a long time limit, so on the long time you will get, you would see even because you just get kind of sort of advected by the slow dynamics, so you would even, you inherit the chaoticity. And this, epsilon goes to 0, this is a long time limit. Plus the whole scaling is a long time limit. But yeah, maybe we can talk about that.
Yes, with respect to conservation, I could believe that there are other quantities you might want to preserve under stochastic perturbations, right? Energy might not be, I don't know.
Divergence.
Yeah, or even, just
I think here what you really want,
more, total angular, or these sort of things, right?
I think what you want here is actually that the debate measure is preserved.
Yeah, sure. In your case, you
Right?
then.
I think that's the next thing I'll try. Assure that the debate measure is preserved.
Let's any more conversation over coffee or something like that.
All right, thanks.
Thank you.